And so every single programming language can simulate a different programming language. And that means that almost every single computer can simulate another computer. And that's the reason why you can have hackers who are like running Doom, which is like a video game, on like a pregnancy test, because that is the ability to execute code. So like anything that can execute code can simulate another thing. And this, I think that that's part of the vast nonsensical things you can do with computers. It's like the possibilities are endless.
Welcome to another episode of Tech in the Arts, the podcast series of the Arts Management and Technology Laboratory. The goal of our podcast series is to exchange ideas, bring awareness, and stay on top of the trends. You're listening to our Art and Code podcast series, highlighting artists working at the intersection of performance, real-time visuals, and live coding. This series is in partnership with the Frank Ratchey Studio for Creative Inquiry at Carnegie Mellon University. My name is Hannah Brainard, my pronouns are she, her, and I'm the lead researcher for AMT Lab. Today, I'm joined by Char Stiles. Stiles is a computational artist, educator, and programmer based in Brooklyn, New York. She works creatively in the lower levels of graphical computational systems and is currently at the MIT Media Lab's Future Sketches group. She's a part of the Livecode.nyc collective, and she co-founded Hex House, an artist studio and event space in East Williamsburg. She has performed internationally, including festivals such as Electric Forest and Mutek Nexus. Char, thank you so much for joining us today. It's great to have you on the podcast. You're a Carnegie Mellon University graduate. You earned a bachelor's degree in computer science and art with a minor in media design. So could you tell us a little bit more about some of your experiences while you were a student at Carnegie Mellon, maybe in the classroom, outside of the classroom, and sort of how that shaped your career path so far?
Oh, it's so exciting. Yeah. I got into Carnegie Mellon for fine art at first. I came in with a painting portfolio. And I basically catfished CMU because I never made a painting since. I basically switched to, I first dabbled in sculpture, and then in one fateful night in Doherty, I just vowed to never be working in sculpture again. I was like making this magnetic wax sculpture, and my hands were like all burned, and I was like, I can't do this. And then I decided, I had actually applied to the School of Computer Science like when I was a freshman, when I was in high school. But I didn't get in, which makes sense because I didn't have any coding experience, and I actually got to read the essay that I applied with, and it was earnest, but also it was clear I had no idea what computers were. I was like, I want to make computers better. And so then I switched to kind of media art and computational code, and switched to computer science and fine art. Yeah. So some experience. There's many more experiences. I've been having a lot of fun being back here and and looking around.
Was there anything sort of outside of your academic experience while you were here in Pittsburgh that you kind of dove into?
I worked a lot with contemporary dancers, Slow Danger, and they're still around. Yeah. They work. Their dance style is called Gaga, and it's like this. They kind of have like a very dramatic lighting in all their performances, and they really like using emerging technologies. And I was also a VJ. I was one of the four. I think at one point I was one of the 3 VJs in Pittsburgh, and it was a great place to get started VJing because nobody had a choice but to hire me. so I got a lot of experience getting started in just in just running AV in different spaces and having that experiencing all the things fail. My first show was at this venue/pizza place, Spirit, and it was a Thursday night, and Lauren Goshinsky booked me, and I think 6 people showed up. It was really fun.
That's great.
Yeah.
So diving into some of your more recent experience, one project that I saw that was really interesting is called Carl, or Code Augmented Reality Live, which extends live-coded visuals onto people's phones in real time. Could you talk a little bit more about that project and some of the software and hardware that went into it?
Oh my gosh, yes. I'm really excited you mentioned this project because I've been dusting it off recently.
Okay.
Yeah, so I made it a couple of years ago. It was a collaboration at first with Char Stiles. We made it at Recurse Center. And then I've kind of, after we built it originally in 3JS and I moved it to WebGL first. And then, I've been iterating on it since then. It's, we use the hosting service /editor /all-in-one web app website called glitch.com. Highly recommend it. It's basically free, and you can have a server, and it hosts it for you, and it's just a really nice, welcoming environment. And so, if you go to glitch.me, fim.glitch.me, you can see what it looks like. Or I think also Carl works, but I have it set up right there at fim.glitch.me, and it uses the phone orientation. It passes that into a shader, which is using a 3D algorithm called ray marching to construct a scene. And also into the shader is imported the camera input, so that can be the pass-through. And then the objects that the ray marching renders is then superimposed over the camera feed, and the direction is of the camera in the virtual world is influenced by the orientation on your camera. So unfortunately, it doesn't have XY transforms. It just has rotation, but it's pretty good. It's good enough to have this kind of just a very to have a bare bones AR experience in live coding. Yeah, and so we first debuted it at Recurse Center in a couple of shows, and then I made it so that you can, the last code comment in the sketch, I'll call it a sketch, is then superimposed over that, so I can talk to the audience by writing comments real time. And I developed that because I did a virtual performance for GitHub, and I wanted to have more control over audience interaction, because virtually, when you're doing something virtually, it's really difficult to kind of get that person-to-person feeling. Yeah.
That's great, and I'm glad that you mentioned that, because kind of reading about your background working, you performed at different festivals, including Electric Forest, and an interview that I thought was interesting is that people will often think that maybe you're the lighting designer in situations like that. So how do you work with the lighting designer and other professionals to ensure that your experience is conveying what you'd like to the audience? Right.
So most of the time when I'm working with lighting designers, it's for an artist that I tour with sometimes. Her name is DJ Dave. She's a live coder artist who writes Sonic Pi. And usually it really ranges. Sometimes the lighting designers, they won't even introduce themselves, and they'll just do their thing, and then they talk to Dave's team, who just tells them okay, her colors are pink and blue, and then I do that. And then sometimes we're right next to each other, and then I follow, was one lighting designer that was in Roadrunner in this venue in Cambridge, no, in Boston, and we really were riffing off each other. She would strobe, I would strobe, and then she would turn green, I would turn green, I would turn blue, she'd turn blue. So it was this kind of this really fun collaboration that really worked out.
That's great.
Yeah.
And collaboration seems to be kind of a big thread throughout your work. You're a member of Livecode.nyc, and you founded Hex House. So could you talk about sort of this collaborative approach and how being part of these groups helps your practice? Yeah,
it really helps me because I'm my worst point is time management, and having other folks be with me in on it makes me feel more responsible of okay, I have to get this done, and it gets me excited about doing the project, because if I'm trying to do something by myself, it's really hard to find momentum, and so these collaborations really are a huge fire and driving force behind a lot of my work. For me, Hex House is a really great place for me to help create one of those spaces.
That's fantastic.
Yeah.
Another space that you're a part of, you mentioned that you're a graduate student at MIT as part of the Future Sketches group in the MIT Media Lab. So could you tell us maybe a little bit about the work that takes place in Future Sketches and your role in that?
Yes. So I started that in September. And it is a space to think about the future of creative coding. So what are the tools that artists are going to be using to creatively make things with code 5 years from now, 10 years from now? And truly, the tools do shape the artwork that comes out of this medium a lot of times. And I like to think about tools as an expression of a way of thought, because you can kind of, when you're making the tool, obviously like your values and the things that you really care about get instilled into that. And so that's a big part of Future Sketches is tool building. Another thing is working just creatively with code. Like, what does it look like to theorize about how light works with code, and think about different languages with code and different interactions with code in the body. I think that's mostly what Future Sketches has been doing. And so things that I've been working on specifically there is I'm working on, well, there's some things that are unreleased that I'm not sure are going to happen. And because I've been there, so it's, what is it, December? It's been like 3 months. I guess it's like a while now. So some things I've been working on there is I'm working on like a presentation tool. So I want like for my presentations to be made through code and art. I mean through code, so that I can kind of have it be like a more controlled environment. And then also I've been working on some experiments with neural radiance fields and Gaussian splatting. And so that's a way to render a 3D model that is a little different than how it conventionally can be rendered, or how to render a 3D scan. And so I've been experimenting with some NeRFs and splats. It's a really interesting way of, I can like nerd out about it. Yeah, cool.
Go for it.
So it's a very interesting way to represent like a 3D scan. Usually like 3D scans up until this point have been sometimes a point cloud, or sometimes it's been like a point cloud that's been turned into a mesh and then that's displayed. But what splats do is it's a way of creating these different Gaussian blurs, so these kind of like ovals of shape with blurred edges, and the splats describe a shape that way, and it just looks a lot better than if you were to just do uniform points wherever the scanner picked up where there's something solid. And then neural radiance fields, aka NeRFs, are a AI model that is trained on the image's input, and the AI model spits out, a bunch of weights that when you give the input of a camera's position, it can render the output of what it looks like from there. And so that is different than other 3D models where it's like you kind of use the graphics pipeline to display things in 3D.
So being sort of in this position, you get to look forward. You get to look ahead at some of the future trends. Is there anything that you see coming down the road? What are you excited about?
Ooh, this is a good one. I might think about this for a little bit. What's coming down the road? Ooh. I mean, I think what's coming down the road is a lot of nichification of different tools. So I like to think that down the road, artists will more and more be able to create their own tools that then they use. So more personalized tools and less Adobe Illustrator and less like, the Adobe monopoly. And also it's like I kind of have to relentlessly believe these things, even if it's sounds very difficult for it to come to fruition. that's the future that I want for artists to be able to be the creators of the tools themselves. Yeah.
That's great.
Yeah.
Tell us about the project you're working on now.
Yes. So the project that I'm working on right now is very unhinged, and it's called the fastest integer multiplier. And it's been like a series of things I've been working on, but it stemmed out of this inspiration from the fact that the fastest integer multiplier algorithm known right now is what is categorized as a galactic algorithm. And what a galactic algorithm is that it's an algorithm that isn't practically used because it's so large. It takes, like, the amount of space that it would take up to implement is astronomical. But it is the fastest known algorithm. So in computer science, there's this concept of big O, which is how fast an algorithm runs for an arbitrary amount of data. And you describe the big O in terms of how big that data is. And so, for example, O of n is that an algorithm runs in linear time. So it only takes that's like iterating through a list of n that is n length. That's O of n. And then there's O of n squared, and which is, you iterate the list that many times, n squared times. You have n squared amount of operations in the algorithm. And so this galactic algorithm runs at O of n of 1.7, I think. And but it only reaches that optimization if the numbers that are inputted that you're multiplying together are bigger than 10 to the 30 digit. Bigger than 10 to the 30. So there's 30 digits there, which is just not practical. When do we need to multiply two integers that have more than 30 digits? Yeah, exactly. Not very practical. But I just think it's hilarious and absurd that the fastest way to multiply integers is using galactic algorithm, and it specifically uses a 1,729 dimensional Fourier transform. And so I thought about, wouldn't it be funny if I attempted to make the fastest integer multiplier in the world just to see where it fails? And so I'm taking this class right now called How to Make Almost Anything, and there's a lot of printed circuit board design in there, and so I wanted to make a hardware fastest integer multiplier. And so I'm starting off by trying to just make a Fourier transform, because that's part of the algorithm in a printed circuit board. And so that's one part of the project, because I'm just going to see where it failed. Am I going to, how far am I going to get? Am I going to actually be able to print part of it? Because in the paper I wish I could quote who wrote the paper, but I can't remember off the top of my head. But in the paper, they kind of sketched out how you could make this integer multiplier with only an 8-dimensional Fourier transform, which is something that is possible to do on a printed circuit board, I think. And the other part of this project is I made a performance that was using Carl. Yeah, so I had people on their phones access a page that I was live coding, and I pretended that this phone was a window into being inside of the largest integer multiplier in the world. And an integer was represented by a sphere. And in AR, they could see the quote-unquote integer in front of them, which was a floating sphere. And then I described how, we are inside the fastest integer multiplier, and I described how it's a series of Fourier transforms, and I described briefly what a Fourier transform is that it's breaking down of frequencies of these numbers. And then I described a Fourier transform. I guess I imagined the visualization of that was a series of toruses within each other, because I think about frequencies as ringlets within each other. And then those were rendered in front of you, and then I was this is in a field of 1,729. And then the field expanded to all of the different Fourier transforms, and then we kind of pranced around that field. So this is, it's kind of I think the reason why I do this is because I make dumb stuff to just talk about these concepts that are, that are usually not put in dumb environments. Yeah, like usually when you hear about Fourier transforms, it's like you're in a signal processing classroom and your very seasoned professor is like telling you about these things. But I think they're funny, and I want to make jokes about them and make AR about Fourier transforms and integer multipliers and algorithms. Just because it's like, you know, if the yeah, just to recontextualize it and to I don't know. I think there's like, yeah, there's validity in that, in being absurd about computers. Yeah.
I love that.
Yeah.
And it makes this very complex thing fun to get involved
yeah,
in.
Yeah.
Interested in.
I think about how at the genesis of computing in Alan Turing's essay, who's like quoted as like the father of computing, he talks about how the genesis is the strive to create a universal solver. And I'm thinking about like what other subjects is in its genesis the goal is to create a universal solver. It's like, okay, there's computer science, right, because it's Alan Turing, and then philosophy and religion. Those are the other two ones. And so like with computation, there are like vastly more silly and nonsensical things you can do with it than things that are practical or make sense. And I think that silliness is very inspiring to get into computation. Yeah. Oh, I could talk forever about that stuff.
I'm like, whoa.
Yeah. Yeah.
That's great.
Yeah, and I think CMU is partially responsible for how the way I am. I took this class called Theoretical Computer Science with this professor, Anil Adab, who I'm going to go see tomorrow to like just be like, thank you for this lecture class. And it was just a lecture class, but I was really inspired by it, so I'm going to go talk to him tomorrow and be like, yeah, it's very inspiring.
That is kind of one of the best parts about being on CMU's campus is, I mean, like brilliant artists, brilliant people in the field of computer science.
Yeah.
It's all happening here and coming together here.
Yeah.
Which is really, I mean, not that many other places in the world can say that.
Exactly. Yeah. It's like if I'm going to be around like, yeah, like when I got into CMU, I was like, if I'm not doing computer science stuff, like, I just really want to see what's up, you know? Yeah.
That's great.
Yeah. Yeah. Oh, I was going to talk about Turing completeness.
Okay.
Are you familiar with that concept?
I'm not.
Okay, so the concept of Turing completeness is that any system that is Turing complete, it can simulate any other system that is Turing complete. And it's kind of like this recursive definition where, and there's also like other things that define it. Like you can write down something and you can read something and you can move ahead. That's basically like what makes something Turing complete. And so, for example, almost every single programming language is Turing complete. And so every single programming language can simulate a different programming language. And that means that almost every single computer can simulate another computer. And that's the reason why you can have hackers who are like running Doom, which is like a video game, on like a pregnancy test, because that is the ability to execute code. So like anything that can execute code can simulate another thing. And this, yeah, and I think that that's part of the vast nonsensical things you can do with computers. It's like the possibilities are endless.
Have you experimented with kind of putting things on silly mediums or?
Yes. So one of the things so I'm a graphics programmer. And so one of the silly things that I did recently was I tried to make ASCII art, but on the GPU. So usually ASCII art is you have your characters and then you make pictures out of the characters. And GPUs are extremely good at making pictures without text. And it's almost like ASCII art was like filling in for the fact that we didn't have any kind of graphics processing, and then GPUs solved that issue, and then I'm bringing this old solution back into GPUs. And so I did that when I only wanted to use just the GPU without having any kind of image import and then like sampling the image. So what I did is I used Lisa Joas curves. I think I might be saying that wrong because it's French. Lisa Joas curves that I pixelated. And Lisa Joas curves are basically just like a sine and cosine line in a 2D plane on an image. You just draw out like if you were to it's like when people swing paint around and it creates that little 8 pattern. It's a Lisa-Joss curve because it can be described by cosine and sine. And so I use Lisa-Joss curves that are very easily computable on the GPU. Then I pixelated them, and then and then I was able to translate other images I made on the GPU to those images by depending on how dark the area was in that part, or in that part of the image. That's how much of the Lisa-Joss curve I drew. And so I created this fake ASCII art, which I can send photos of if you're interested.
Oh my goodness, that'd be fantastic.
Yeah, great.
Well, thank you so much for joining us today. It's great to kind of hear more about your story and your background.
Yes, thank you so much. It was so great to meet y'all.
Thank you for listening to the Art and Code series on Tech and the Arts. Be on the lookout for new episodes coming to you very soon. If you found this episode informative, educational, or inspirational, be sure to send this to another arts or technology aficionado in your life. You can let us know what you think of this podcast by visiting our website, amptlab.org. That's amt-lab.org, or you can email us at amptlabcmu@gmail.com. Follow us on Instagram at Tech in the Arts, or Facebook and LinkedIn at Arts Management and Technology Lab. We'll see you next time.